Hi, today I'm talking about Leet Code problem, 1343, number of subarrays of size k and average greater than or equal to threshold. And so what this problem asks you to do, it wants you to take an array and a k and a threshold value and return the number of subarrays in the array of size k with an average that's greater than or equal to this threshold value. So in their example number 1, they say 255 has an average that's greater than or equal to 4. Obviously that would be an average of 4. 555 has an average greater than or equal to 4. Obviously that would have an average of 5. And 558 has an average greater than or equal to 4. And so you're just supposed to return the number of subarrays that have an average greater than or equal to your threshold value. And so I guess one thing I want to say right at the beginning is it's important to fully read and kind of understand the problem, because when I saw it, I immediately thought of a YouTube video that I had recently watched about something called, I believe it's Kadane's algorithm. And Kadane's algorithm is about how to find all the subarrays of an array. And so I had recently watched Kadane's algorithm, and I see this problem says find all the subarrays. And so I immediately think, Kadane's algorithm, I can use that. But of course, Kadane's algorithm isn't needed at all. So it's really just a danger of kind of knowing a little bit about the problem and not being careful enough when you think about the problem. So that was kind of a long digression, but let me jump into how I solved this. Oops. Well, I lost my pencil, so I won't draw it. But how I solved this problem is I at first thought, well, maybe I can use a dictionary, and I'll just keep track of the numbers that are in a kind of sliding window. So I only need to consider subarrays of size k, and that's why you don't need Kadane's algorithm. You don't have to figure out what all the subarrays are. You just have to figure out what's the next subarray of size 3. And obviously that's just 3 down from your current index. Or size, 3 down from your current index. So there aren't that many subarrays of size 3. And you just check each one and see if its average is greater than or equal to 4. So I thought, okay, I can use a dictionary summing up the count of each element, and then I'll just take a 2 out of my dictionary and add another 2 to it, take a 2 out, add a 5 to it, and so on. And then I can just sum up all the values in my dictionary and produce the average. But while I was thinking about it, I realized, the dictionary is kind of an efficient way of sliding my window along, taking a number out and putting a new number in, rather than having to compute every individual subarray. The dictionary is kind of an efficient way to do that, but we can be even more efficient when you realize that an average is just the product of the threshold and k. So like the number that you need to be greater than or equal to is a product of threshold and k. The implementation I have this variable sum so far, which is going to be what's the sum of my sliding window. And so rather than keeping track of a dictionary with all the numbers in it, I can just keep track of the sum of the numbers I'm looking at as I kind of slide my window along. So the first thing I'm going to do is read in the first k values of my array. And then I'm doing that in lines 5 and 6. I'm saying for I in range k, sum so far increases by the value at array sub I. So we build up 2 plus 2 plus 2. So our sum so far is 6. And basically we're just going to check, is 6 greater than or equal to the product of k and threshold? Because if it's greater than or equal to this product, then we know the average of our sum so far would be greater than the threshold. And so the reason for comparing the product as opposed to just dividing and finding the average every time is that it saves us a division. We only have to do one multiplication compared to having to do one division per subarray. So I hope that makes sense. So here on line 8, I'm calculating what I call my cutoff, so my threshold product k. And my start, I'm going to start at index k, because I've already read in the first 1, 2, 3 values. So the next value I'm going to deal with is this one at index k. And my result, this is the value that I'm going to return. I'm going to evaluate this Boolean expression, so sum so far is greater than or equal to cutoff, is the sum that I've currently built up with the first k values greater than or equal to cutoff. If it is, I want a 1 out of it, and if it's not, I want result to start as 0. And so evaluating this Boolean expression as an int, which is what I'm doing here on line 10, will say if this evaluates to true, it's going to be a 1. If it evaluates to false, it'll be a 0. And so then I'm just going to have a loop while my start is less than length of array. I guess it could easily be a for loop as well. We can, get rid of one line here. Let's see, we want to say for, well, now that I think about it, I already, I guess, well, whatever. I'll just say start in range k through len array. I don't think that's any different than what I had, but we're not using a while loop. And we can take out this one line to simplify it slightly. I hope that'll still work. Oops. Of course, I forgot my colon. Anyway, so what I'm doing inside of the loop is I'm going to increase sum so far by the start value, which remember is starting at k, so 3 in this example. So my sum so far is 6, so I'm going to increase it by the new value, and I'm going to decrease it in line 12 by k back from my start. So 3 back, kind of like the other side of my sliding window. So in this case, as I slide my window from 222 to 222, it'll stay exactly the same. But when I slide my window again to 225, I'd be taking out a 2 and adding a 5 to my sum so far. And then I'm just going to make this check. If sum so far is greater than or equal to cutoff, we're going to increment the result. And that's the same check that I do right here in line 9. And here in my comment, I was just testing to see if it's faster to increment result by this one Boolean expression. I thought, well, maybe this will be faster for some reason. But in the 2 tests I did, it wound up being slightly slower. But I don't know if that's just because LeetCode times are different kind of every time you run them, or if it is actually slower or faster to increase result like this as opposed to doing this 2-line thing. Who knows? I think ideally I would like to do it like this, just because it kind of is fewer lines and it removes a branch. But it's slightly slower, so I didn't do it that way. And then, yeah, we just return the result. And so then the final thing I wanted to, well, I guess first I'll talk about the test cases. Basically, I just used their 5 examples as test cases. So those gave pretty good coverage, I felt. I would also usually, ordinarily, do the test cases of the constraints. So what if we had 10 power 5 array size? I would try to hit these constraints, but I didn't because I knew that this is going to be a pretty fast solution. Like, I can't imagine how it could possibly be faster. So I just thought it's probably good enough for the big sizes as well. I can't imagine how it could be any faster. So if it was bad for the big sizes, I'd be in trouble. And yeah, the final thing I wanted to do was show, actually here, let me show running it first. When I run it, it produces a result something like 60 to 70 percentile for speed. Of course, now it produces 90. So I was curious how I could get even faster than it was. When I ran it before, it's down here at 600, 700 milliseconds. And here is where I'm trying to mess around and figure out, is this faster than this? So I was trying to say, this is a simple problem. How could it possibly be any faster than this? And I don't know that it can. I think this is just an example of LeetCode having random variants. So like I looked in the forum, and this one says it's Python beats 90%. But we can see that it's actually slower than my implementation because, for example, they're doing one division. Like they're calculating the average, this person is. So they're doing one division for each execution of their loop. Actually, as I look at it, yeah, increase if s over k is greater than threshold. So like they didn't do the trick of calculating the cutoff. They're doing a division every execution of their loop. So that has to be substantially slower than what I have. I guess one thing I could do is just copy it and see if it does beat 90%. Although mine beat 90% right now. Well, whatever. I won't mess around with this on on video. No, actually, just kidding. I will. I'm just curious. I'm just curious what other people are doing. Yeah, if you're not curious in this, by all means, this is the end of the video, as I'm sure you can tell. Thanks for watching. Click like if you enjoyed it. Leave a comment to let me know you're watching. And yeah, I'm trying to work through a LeetCode problem a day or something like that. And I'll probably be talking more about other kind of hobby or side projects I'm working on. So if you're curious to see those, you may want to subscribe. But yeah, either way, thanks for your time. Right, now we'll get to the secret after video treat of running this person's solution and seeing if it is legitimately faster than 90%. If it's faster than my solution, I'm going to be quite upset. Quite upset. Okay. $668. So it's about the same as my original solution. I guess it's kind of an argument that taking out the division part doesn't really change things. Let's see, what is this sum s? Let's just make sure that still works. So something he did, well, maybe there's a little savings, or maybe it is purely random. 648. Yeah, I think it's just random, or like the difference isn't big enough for, well, whatever. Anyway, that's the end of the video. Thanks for watching. Bye-bye.